I am Gulab Chand Devangan from IUCAA in Pune. In this lecture, I will be discussing on X-ray astronomy. So, let us ask few questions on X-ray astronomy. So, first of all, what are X-rays? What are their properties? How are X-rays produced? How do X-rays interact with matter? X-rays were discovered quite by an accident by Rontgen in 1895, when he was studying phenomena associated with electric discharge in gases. Working with cathode ray tubes, Rontgen observed faint glow in a nearby fluorescent screen. The tube Rontgen was using was a glass tube with positive and negative electrodes encapsulated in it. When he applied high voltages, he observed this faint glow in the nearby fluorescent screen. He suspected this may be due to the light generated in the tube. So, therefore, he blocked the tube by thick black paper. Still he observed these faint glows, and he named this unknown faint glow as X-ray radiation. After discovering X-rays, Rontgen found the characteristic of X-rays very quickly, and he showed that X-rays pass through material made up of lighter elements such as paper, wood and aluminum, but X-rays are stopped by heavy elements such as gold. This picture is the first X-ray picture of Rontgen's wife, Mrs. Rontgen's hand. In this picture, you clearly see the bones and the ring, the gold ring. So, thus demonstrating that X-rays pass through easily through lighter elements such as carbon and oxygen in the flesh, while many X-ray photons are absorbed by calcium in the bones, while X-rays are completely absorbed by the gold ring, which is a heavy element. So, what are X-rays? So, X-rays are electromagnetic radiation just like light, but they are something like 1,000 times more energetic than optical photons. So, X-ray band is very wide, and it is defined by photon energies which is greater than the photoelectric cutoff due to intervening hydrogen, and less than the 511 keV, which is the electron and positron annihilation line energy. So, X-ray band is generally considered in the range of 0.1 to few hundred keV. In this picture, you see the visible band is very tiny fraction of the entire electromagnetic wave band, while X-rays contains actually a large fraction of this electromagnetic wave band, and hence it has it contains lots of information as well. How are X-rays produced? As I said, X-rays are 1,000 times more energetic than optical photons. So, therefore, X-ray production requires highly energetic particles or very high temperature. In astrophysics, in cosmic settings, X-rays are produced by three main processes. The first of these is thermal Breslin emission, the second is synchrotron emission, and third is inverse Compton emission. These processes give rise to continuum X-ray radiation. There are also processes which give rise to X-ray line emission, which is essentially due to transition in inner atomic cells. We will go through each of these processes one by one. The thermal Breslin emission. Consider a hot gas with a temperature of about 10 to the power 6 Kelvin or more with a low electron density, so that it is optically thin and transparent to its own radiation. At such a temperature, the atoms are ionized. So, the gas will have free electrons which are negatively charged, and positively charged ions and protons, of course. In such a situation, if an electron passes close to a proton or a positively charged ion, the electric force causes this electron to change its path, and the electron is accelerated. Such an accelerated electron gives rise to X-ray radiation. In a thermal gas with this kind of temperature, the distribution of electrons is essentially Maxwellian, and this Maxwellian distribution of electron results in continuum radiation with a characteristic shape which has an exponential cutoff, and this exponential cutoff is determined by the temperature. And if the if the particle energies are high, that means the temperature are high, then the photon energy from the thermal Bremsstrahlung emission are also high. So, if the temperature is high, the spectrum extends to higher energies. In addition to continuum radiation, in the hot gas can also give rise to a number of emission lines, because if the gas is ionized, particularly at a given temperature, let us something like 10 to the power 6 Kelvin, the heavier elements will not be fully ionized. So, in such a case, if an electron moves close to one of the partially ionized atoms or ions, then it gives some energy to this ion. Thus, the ion ends in a higher excited state, and in this ion remains for a very short time in such a higher excited state, and it de-excites to one of the lower level, giving rise to radiation which is characteristic for this kind of transition, and therefore, the line radiation. The second process is the synchrotron emission. If an ultra relativistic electron passes through in a medium containing magnetic field, then the electrons will in general spiral around this magnetic field lines, because the direction of the motion of the electron is changing. Therefore, the electrons are accelerated, and this acceleration causes radiation in radiation. And if the energy of the electrons is very high, that is ultra relativistic, this radiation comes into the X-ray band. The frequency of this radiation from a single electron moving in a magnetic field depends on the energy of the electron through this Lorentz vector gamma, and and on the magnetic field in which the electron is moving, and the direction of the motion of the electron with respect to the magnetic field through this angle alpha. And the spectrum from the single electron picks at this frequency nu 0, given by this expression here. In general, in astrophysics, there is usually a power law distribution of electron energies. So, if a single electron has this kind of a spectrum here, then the electrons which have power law energy distribution will give rise to different kind of this single electron spectrum. And if you sum over all this single electron spectra, what you will get is a power law spectrum over a broad energy band. This is the characteristic of synchrotron radiation. In addition, synchrotron radiation is also polarized. So, if you are observing a broad band spectrum and significant polarization, then we are almost sure that the radiation must be synchrotron radiation. So, how does this power law distribution of electron energy corresponds to the particular shape of the spectrum? Let us say if the electron energies are distributed in the form of a power law with a power law index of this minus p, then the electron spectrum is, as I mentioned, is a power law with this shape nu to the power alpha, where alpha is the spectral index and is related with the power law index of the electron energy distribution with this expression alpha is equal to minus p minus 1 by 2. So, if you know the power law distribution of electrons, then you can then you also know the shape of the power law spectrum of the synchrotron radiation. The third process is the inverse Compton scattering. In this process, an ultra relativistic electron, when it collides with a low energy photon, meaning for example, radio photon or infrared or optical photon, in such a process the ultra relativistic electron imparts its energy to the low energy photon, therefore pushing the photon energy to the X-ray band. This is essentially the inverse Compton scattering or Compton up scattering. This in astrophysics, hot plasma is quite common. So, if you have hot plasma, that means you have ultra relativistic electrons and magnetic and low energy photons are also quite common. For example, cosmic microwave background radiation. In such a situation, if the low energy photons are interacting with the hot electrons in the hot plasma, then the expected spectrum is again a power law but with a cutoff at high energy, which is a characteristic of the temperature of this hot plasma. What happens? Let us imagine the low energy photon has a simple black body spectrum. So, in such a case, if this simple black body spectrum is interacting with a hot plasma with about 100 keV temperature, then a fraction of tau, where tau is the optical depth, is upscattered to higher energies in one scattering process. So, in the secondary in the second scattering step, this again this fraction tau of this radius the photon spectrum is upscattered to higher energies, and this process continues due to the multiple Compton scattering. And if you add all this spectra over the energies, then you get a power law which cuts off at higher energies, because the photons cannot gain energy more than the energy of these electrons. Therefore, this cutoff. The three processes I mentioned, those essentially give rise to continuum radiation processes. In addition, there are line emission in the X-ray domain due to the transitions in the inner atomic levels. One particular process which is very important in astrophysics is the fluorescence line emission. In this process, what happens when a high energy photon interacts with an atom or an ion, it ejects the electron from the innermost cell, and therefore it creates a vacancy. And an ion or an atom with such a vacancy is in an excited state. So, what happens next is that one L cell electron actually jumps to the K cell, which has a vacancy, and this transition creates a photon which results in the fluorescence line emission. The next question we will address is, how do X-rays interact with matter? Suppose a beam of X-ray radiation is passing through a slab of material, and in this process some of the photons actually disappear from the beam, and there is no gradual loss of photon energy. Photons disappear some of the photons disappear altogether. So, if the incident beam has an intensity I0, the transmitted beam will have an intensity I0 and e to the power minus mu x. So, intensity has reduced by this factor e to the power minus mu x, where x is the thickness of this slab and mu is the absorption coefficient. If you are talking about interaction of X-rays with the solid material, we usually talk in terms of the densities and thickness in terms of gram per centimeter square, and then the absorption coefficient becomes mass absorption coefficient. In astrophysics, we measure thickness in terms of number of atoms NH per centimeter square column extending from the source to the observer, and this NH here is called the column density, and the absorption coefficient becomes the cross section. So, therefore, the intensity reduces by the factor e to the power minus sigma NH. X-rays in general interact with different processes at a low energy, particularly below 50 keV. X-rays interact with matter through this photoelectric absorption process. What happens here? A photon is absorbed and an electron is ejected with an energy which is the energy of the photon minus the binding energy of the particular atom. The absorption cross section varies with energy as e to the power minus 3, and this figure essentially shows this absorption coefficient. How does the absorption coefficient varies with energy? This absorption coefficient or the absorption cross section decreases as e to the power minus 3, but when the energy is high enough to eject one of these electrons, the absorption cross section suddenly jumps up, causing the absorption edges in the observed spectrum. And if you see the absorption spectrum due to intervening medium or interstellar medium, you will see a number of these absorption edges, which are the signatures of the material present in the interstellar medium. In addition to photoelectric absorption, the other important process in X-ray band is the Compton scattering, particularly above 50 keV. In this process, X-ray photons scatter individual electrons within an atom. The energy of the incident X-ray is shared between the scattered photon and the electron. This figure here shows the relative importance of these processes, photonic absorption and Compton scattering. In addition, at higher energies in the gamma ray band, there is another important process called pair production, but it is not, it is important in gamma rays, but not in X-rays. So, at the low energies below 50 keV, the photonic absorption cross section dominates. At hard X-rays, the Compton scattering dominates, and at gamma ray energies, the pair production dominates. In the next part of this lecture, we will address the following questions. What is X-ray astronomy? Where are the X-ray observatories? What is the difference between X-ray astronomy and medical X-rays? And what type of detectors and telescopes are used in X-ray astronomy? X-ray astronomy is essentially the study of X-rays that come from cosmic sources in the universe. Sources such as our sun, X-ray binaries, supernova remnants, active galaxies, galaxy clusters, etc. Here is an image of a galaxy NGC 4697, which was taken with the Chandra X-ray observatories, and this galaxy, like other galaxies, shows a large number of point sources as well as diffuse X-ray emission. We will talk about some of these sources in this lecture. The next question we want to ask is, where are the X-ray observatories? You may be aware that atmosphere is opaque to X-rays. So, X-ray astronomy is done using satellites, rockets, and at the highest energies only with balloons. Here this figure shows the altitude at which the electromagnetic radiation in different bands reach above Earth's surface. So, here the soft X-rays reach up to only about a few hundred kilometers above Earth's surface, while hard X-rays can reach down to about 20 or 25 kilometers. So, this hard X-ray astronomy can be done with balloon-borne experiments, while to study soft X-rays from cosmic X-ray sources, we need to use satellites and rockets in the medium energy X-rays. What this means is that because the X-ray detectors have to be in satellites above the Earth's atmosphere. So, therefore, X-ray detectors have to work right at the first time. We cannot go and fix them there. So, any problems have to be understood remotely and calibrated accordingly. So, because of this reason, X-ray astronomy experiments are very expensive, and there are not many X-ray observatories in the space. Some of the observatories which are operating currently are listed here. The Chandra X-ray observatory, launched by NASA in 1999, it provides fantastic imaging resolution and fantastic images of various cosmic X-ray sources. The XMM Newton is the ESA mission, again launched in 1999. It is a high throughput X-ray observatory and excellent for X-ray spectroscopy in the 0.3 to about 10 kV band. The SWIFT mission, which was launched in 2005, and is an excellent observatory for transient sources such as gamma ray bursts. The Nustar mission by NASA was launched in 2012. This is the one satellite which is sensitive, which has the hard X-ray optics and sensitive in the hard X-rays from 3 to 80 kilo electron volt. Astrosat is the Indian multi-wavelength astronomy satellite. It is sensitive from optical to all the way to hard X-rays to few hundred keV. Astrosat was launched in 28 September 2015. We will discuss more about Astrosat towards the end of this lecture. Many people ask this question, what is the difference between medical X-rays and X-ray astronomy? In medical X-rays, in doctor's office, usually there is an X-ray generator at the one end, and a few meters across there is a camera which records the X-rays from this the X-rays generated from this X-ray generator or X-ray source. A body part such as the hand which is to be examined is kept in between this in the X-ray camera and the X-ray generator. X-rays pass through this body part, or some of them get absorbed, and that creates an image in the camera, and the doctors essentially examine this image and find any defects in the bones and all that. In X-ray astronomy, the X-ray generator is replaced by a cosmic X-ray source which is very far away, and this cosmic X-ray source essentially gives rise to X-ray radiation which pass through the intergalactic medium if it is outside the galaxy, and as well as the interstellar medium before reaching above the Earth's atmosphere, where our X-ray observatories are kept. This observatory will have an X-ray, may have an X-ray optics as well as a detector, and essentially collects the X-ray radiation from this cosmic X-ray source, and it may produce an image, spectrum, or even a time series of the X-ray photons, which astronomers essentially analyze and infer or investigate the nature of this cosmic X-ray source in X-ray astronomy. So, what kind of X-ray detectors are used in X-ray astronomy? Initially, X-ray astronomers use the simple proportional counters. What is a proportional counter? Essentially, it is a gas filled detector. It has a gas filled chamber fitted with an X-ray transparent windows. So, X-rays pass through this window and interact with this the gas contained in this detector. Usually, this detector is filled with xenon, for example. So, what happens, the X-ray photon interact with this xenon atom and eject one of the electron from the innermost cell. This electron is attracted towards anode where a high voltage is applied. So, therefore, this the electron is attracted due to this electric field of this anode. In this process, electrons gain energy and ionize other atoms. So, one electron, while generated by the X-ray photon, when it moves closer to the anode, it creates large number of other electrons. So, therefore, there are bunch of electrons or electron cloud generated from one single photon, and which is essentially collected at the anode wire, and that is how X-rays are detected in proportional counters. One of the satellite mission which has this proportional counter is this Rossi X-ray timing explorer, which was launched by NASA, and it operated with, from 1995 to 2012, and it produces many excellent results in X-ray astronomy. It contained 5 proportional counter units called as PCUs. These proportional counter units had this collimators, so that the field of view could be limited using these detectors. So, here is an example of this collimator. It is called the honeycomb collimator. So, X-rays through these collimators, the X-rays coming from the certain field are essentially detected by this proportional counters. X-rays coming out of that field of view are not detected by the collimators. They are essentially absorbed in the collimators. These proportional counters were workhorses in X-ray astronomy. They are still being used, but later on more sensitive telescopes and detectors were required, and this was achieved with focusing X-ray optics and semiconductor detectors. There are several advantages of using focusing X-ray optics as well as semiconductor detectors. If you have focusing X-ray optics, you do not need large collecting area or you need large collecting area, but not large detectors. If you have large detectors, it can create a large amount of unwanted background. So, in the focusing optics, you need very small size detectors. So, therefore, reducing the background. Therefore, improving the signal to noise of these observations. And obviously, once you have X-ray optics, you have the capability to image the X-ray sources. So, therefore, distinguishing X-ray radiation from one source to another source, also enabling us to study the spatial distribution of X-ray radiation from a given source. X-ray reflection. X-rays are not easy to reflect unlike optical radiation. If X-rays are incident normally like in an optical mirror, then X-rays are completely absorbed, they are not reflected. X-rays can be reflected with only in one condition, using this principle of total internal reflection. Imagine there are two mediums with refractive indices n1 and n2, and the light, optical light is incident in one of the medium at an angle alpha 1, and then this radiation will be reflected as well as refracted with an angle alpha 2. So, in this case the Snell's law is essentially sin alpha 1 by sin alpha 2 is equal to n2 by n1. Or write down the relative reflective index as n. If the refractive index of the first medium is greater than the refractive index of the second medium, then in that case one can write this Snell's law as sin alpha 2 equal to n1 divided by n2 and multiplied by sin alpha 1. And this number, if n1 by this number will be more than 1 for large alpha 1 if n1 is greater than n2. So, essentially if you have large alpha 2, then there would not be any refraction. So, one can define a critical angle alpha 1 c for which alpha 2 is 90 degree. So, in this case one can write sin alpha 1 critical angle equal to n. N is defined as the ratio of this refractive indices n2 by n1, or one can write the same expression as cos theta 1 is equal to n, where the theta 1 is the grazing angle and it is 90 minus alpha 1. Okay. For visible light, this refractive index of the first medium is 1.33 for the glass and n2 is equal to 1.0 for the air. So, therefore, the critical angle alpha AC becomes 48.8 degree. So, this principle is called the total internal reflection, as the reflection is internal to the medium. If you consider X-rays, for X-rays the refractive index is less than 1 for all material, while it is 1 for vacuum. Thus, X-rays are traveling through vacuum and impinging on a material surface, and with this total internal reflection, using this principle, X-rays can be reflected provided the grazing angle theta 1 is very small. In case of X-ray reflection, this process is called total external reflection as it occurs outside the material medium. One can draw an analogy of this X-ray reflection with the skipping stones in the water. So, this grazing angle, if it is very small, then X-rays can be reflected. So, here in this figure, the reflectivity for X-rays as a function of incidence angle is shown. As you see here, if the grazing angle is very small, less than about 0.2 degree for silicon, then the reflection is close to unity, while for larger grazing angle, the reflection is almost 0. Same for other material, but depending on the atomic number of the material, the X-ray the angle of incidence can be slightly larger. So, if we want to make mirrors, one has to use this principle and require that the grazing angle is very small for X-ray reflection. Using this principle, X-ray telescopes have been constructed, but you need two X-ray mirrors, one with the paraboloid shape and another one with the hyperboloid shape. So, such a configuration is called Walter 1 geometry. So, the X-ray incident X-rays are reflected once through the paraboloid mirror and second time with the hyperboloid mirror, and finally, they are focused onto a focal plane. In order to increase the effective area of such a telescope, one needs to have large number of these mirror pairs. So, here you see an example, which is the example of the Chandra X-ray telescopes. There are 4 mirror pairs, the incident X-rays which are parallel, they are incident, they are reflected twice by these mirror pairs, and they are focused onto a detector, which is here, which is a CCD, or charge coupled devices here, and the X-rays are imaged onto this particular charge coupled device. How does CCDs work, charge coupled devices? The charge coupled devices are essentially pixelated semiconductor detectors. So, the photons interact with one of the pixel, then generate the charge. Those charges are collected and transferred and read out. In the X-ray CCDs, there are two parts. One is called the image section, and another part is called the store section. The store section is shielded from illumination. So, what happens? The X-ray photons interact with the pixels in the CCD in the image section. Those charges generated are transferred to the store section and finally read out. In such a detector, one can read out the amount of charge created by individual X-ray photons, which is a measure of the X-ray photon energy. One can also measure the arrival time, or the time of the interaction of this X-ray photon with the detector, as well as the direction of these photons using the X-ray optics. So, one can create X-ray images, the X-ray spectrum, as well as the light curve or time series of X-ray photons. These are the tools, or the means to study the nature of X-ray sources. Next question we want to ask are what are the various types of X-ray sources in the universe? Our sun is an X-ray source. In fact, it was the first astronomical X-ray source which the X-rays from which were discovered. So, the first astronomical X-ray experiments were performed in the US in 1948 and 1949 using the captured World War II rockets. So, these rockets essentially contained Geiger-Müller counters, and they could detect X-rays. So, X-rays were detected from the solar corona, which is essentially the hot outer layers of the sun's atmosphere. Though sun was X-ray emitter, but the amount of X-ray emission was very weak. So, sun gives rise to very weak X-ray emission, and if you look at the total luminosity in the X-ray band, that is about 1/1,000,000th of its total energy radiated in the optical or ultraviolet, optical and ultraviolet and infrared bands. So, because of this issue that our sun being so close has so minute amount of X-ray radiation, the stars which are much further away will not be detected in the X-ray band available with the technology at that point of time. So, therefore, at that point of time, many people thought that X-ray astronomy cannot be done in fact. One breakthrough experiment was performed in 1962. The experiment was performed to study X-ray radiation from the moon, which would be the reflected X-rays, reflected solar X-rays by the moon. So, a rocket was launched in 1962, and this was a spinning rocket. When the rocket spun the field of its field of view, then there was a sudden increase in the count rate from the counters counting detectors used, and this increase in count rate was due to a source in the Scorpius constellation, and this was the first X-ray source in that constellation, and it was named as Scorpius X1 or SCO X1. Further rocket experiments in the 1960s found other X-ray binaries as well as identified X-ray emission from several supernova remnants from M87, the Galaxies, Cygnus A, and the coma clusters of galaxies, and thus X-ray astronomy was born. What was this source, the first X-ray source, SCO X1? It was very strange source because none of the other stars had this much X-ray radiation. When optical spectrum of this source was studied, the optical spectrum of SCO X1 was essentially had a blue optical continuum. with emission lines of hydrogen and ionized helium. This kind of spectrum was very, very different from the optical spectrum of normal stars, which usually have absorption lines and weak continuum. So, this indicated that the blue continuum and the ionized lines of helium and hydrogen essentially indicated a source of ionization which must be very hot, but the nature of this source was still not known. Uhuru's X-ray satellite played an important role in understanding the nature of these sources. So, Uhuru discovered two pulsating X-ray sources with precise periods. These sources were Centaurus X1 and Hercules X1. So, the pulsations with precise periods essentially demonstrated that these sources must contain rotating neutron stars, as the periods were very, very short. These sources also showed X-ray eclipses. So, this indicating or demonstrating that these sources must be binary stellar system in which one of the component must be a neutron star. The binary systems giving rise to X-ray radiation, strong X-ray radiation, are known as X-ray binaries or X-ray binary systems. In these binary systems, one of the object is a neutron star. For example, in Scorpius X1, Hercules X1, or Centaurus X1, and the other star is a normal star. In general, the compact object can be a white dwarf, a neutron star, or a black hole. What happens is that the compact object with its gravity accretes material from the normal star, and this accretion process results in a strong X-ray radiation, and these objects are essentially laboratories to study accretion physics and very strong gravity near the compact objects such as neutron star and black holes. The other kind of X-ray sources are supernova remnants. What are the supernova remnants? Supernova remnants are essentially remnants of huge explosions known as the supernova explosions. So, essentially stars more massive than about 10 solar mass end their life in supernova explosions as the nuclear fuel runs out at the end stages of the stars. As a result of this supernova explosion, these materials or the cells of around this cells of the stars are thrown out with large speeds, tens of thousands of kilometers per second, and these material with a high speed generates shocks and heats the material, which is hits the material with which result attains a very high temperature, million-degree Kelvin about. So, which gives rise to this X-ray radiation, and you see their cell kind of structure. This is essentially the supernova remnant observed in the X-ray band by Chandra X-ray telescopes. This is the image, X-ray image of the supernova remnant along with this central neutron star of this object RCW 103, which is 10,000 light years away. The neutron star at the center rotates once in about 5.7 hours. Another famous X-ray source is the Crab Nebula and the Pulsar. In this case, a pulsar, fast rotating neutron star, gives rise to this particles. This pulsar and is again a result of this supernova explosion, which happened in 1054 AD. So, what happens? This rotating neutron star with this strong magnetic field works like a huge battery, and it ejects particles along along its poles. These relativistic particles are moving in the magnetic field, and therefore giving rise to the synchrotron radiation in the almost over the entire wave band. In the X-ray emission comes from the central regions, because synchrotron X-rays require highly energetic particles. So, their lifetime is less. So, the particles when they are thrown out of this by the neutron star, they generate the X-ray radiation, the synchron radiation. They lose their energy, move out, generating the radiation in the optical band and also in the infrared band. This is the composite image by NASA's great observatories, the Chandra in X-rays, HST in the optical, and Spitzer in infrared. The other strong X-ray sources are this active galactic nuclei. What are these? These are nuclei of galaxies which are active in some sense. Okay. So, these nuclei of these active galaxies produce huge amount of power, electromagnetic power, which are observed in almost entire electromagnetic wave band. Here is the HST image of this NGC 1365, one of this active galaxy. You see the central region is very bright. Okay, and there are dust lens which are passing through the central region. So, nucleus is though it is bright, but it is not very obvious due to this dust lens. But in X-rays, there is a very bright X-ray source which is due to this active nucleus in this galaxy NGC 1365. In this image, there is another galaxy, another active galaxy, and this image was taken with Astrostatistics ultraviolet imaging telescope. Here you clearly see very bright star like nucleus. This is a clear signature of the active nucleus in this galaxy. So, what are these? These are essentially these active galaxies essentially contain supermassive black holes at the center, and these supermassive black holes accrete material and form an accretion disk, which shines in the optical ultraviolet, giving rise to this very strong optical UV radiation. These objects can have very strong relativistic jets, particularly observed in the radio band, but also in the optical and X-ray bands. These active electric nuclei are very strong sources of X-ray radiation, and the X-ray radiation in these objects arises from very close to the central supermassive black holes. Therefore, X-rays become very important tool to study the strong gravity near the central supermassive black holes. And there are observational signatures which allow us to study the strong gravity near the central supermassive black hole. One example is this broad fluorescence iron line which arises from these active galaxies. So, what happens? Let us go through the very basic process. So, the supermassive black hole has an accretion disk around it, and this accretion disk is rotating, and the iron line emission arises from this inner regions of the accretion disk which is rotating. So, if you consider these rings in the accretion disk, and because of the rotation and because of the this Doppler shifts, this rotating disk gives rise to this double horn profile. Just using Newtonian physics, one can infer this kind of thing. Okay. Because the disk is rotating very fast with relativistic speeds, so one has therefore one has to use special relativity to infer the line profiles. And once you use special relativity, due to the relativistic beaming, the higher energy side of this hump is increased, while the red wing of this line, or red side of this hump is reduced, because the emission is beamed away from us. And because the line emission is arising in the immediate vicinity of the supermassive black hole, one has to use the effects of general relativity. And the general relativity, what it does, it shifts and broadens the entire line and it shifts the line to the redward side. And if you sum such line emission from all the rings, then you get a broadened skewed relativistic iron line which looks like this. And such a line profile was actually observed by the Japanese X-ray observatory known as ASCA, the Advanced Satellite for Cosmology and Astrophysics, and which has X-ray optics and charge coupled devices. Such advanced technology enabled to measure the line profile, and which was consistent with that expected from line emission around the supermassive black hole, and broadened by special and general relativistic effects, thereby allowing us to study general relativity here. Using this broad iron line, one can actually measure the spin of the black hole, how fast the black hole is actually spinning. So, because using the red wing of the line, one can determine the inner extent of this accretion disk, and the inner extent of the accretion disk depends on how fast the black hole is spinning. For example, if the black hole is not rotating, that is the Schwarzschild black hole, in such a case the disk is truncated at 6 times the gravitational radius, while it is rotating very fast, a curved black hole, the accretion disk will be truncated at about 1 RG. So, the line emission you expect from even more innermost regions, and therefore, broader line emission compared to the line from around this Schwarzschild black hole. So, by using the red wing of the broad iron line, one can actually measure the spin of the black hole, and that has been done for a number of objects. Here is one example, another one Seyfert-1 galaxy MCG 52316, and these are the line profiles observed from this source, and in this case the spin of the black hole is consistent with 0. That means, the black hole is not really rotating in this particular case. While in another case, another Seyfert-1 active galactic nucleus MCG 63015, the iron line is so broad that it requires line emission from within the 6 RG radius, which is the limit for the Schwarzschild black hole. So, you need line emission from down to about 2 times the gravitational radius RG, and it suggests that the black hole is highly spinning in this particular case. Another kind of very interesting objects in X-ray astronomy are these galaxy clusters. So, what are the galaxy clusters? These are essentially groups of galaxies. The galaxy clusters contain large number of galaxies and are bound by their mutual gravitational attraction, and are the largest gravitationally bound objects in the universe. This image essentially is the optical image, or the image in the visible light of one of the galaxy cluster known as Abell 20229, and you see a large number of galaxies and the central galaxy as well in this cluster. If you look at, or if you observe the same cluster in the X-ray band, then what you see is shown here, the X-ray image. You do not see the individual galaxies in the cluster, but what you see, a diffuse X-ray emission filled the entire region of the galaxy cluster. So, the diffuse X-rays are produced by hot gas in the cluster. So, this hot gas is essentially confined to the cluster primarily by the gravity of this dark matter. With the observed X-ray radiation, one can measure the temperature of this gas, and therefore, one can find the depth of the gravitational potential and the total amount of matter, and this is how one infers the presence of dark matter in the inner regions of the galaxy. In the last part of this lecture, we will discuss about this Indian astronomy satellite called as Astrosat. So, we will essentially discuss what is Astrosat, what kind of instrument it carries, what are the recent results from this mission. Astrosat is the first multi-wavelength astronomy observatory in space, and it is an Indian mission launched by space, and it is the result of an effort of large number of people from large number of institutes. It carries multiple instruments. In the optical ultraviolet band, there is an UVIT ultraviolet imaging telescope, which has a fantastic imaging resolution of about 1.4 arc second. It is sensitive in the from the optical to far ultraviolet region down to about 1300 angstrom. Okay. In the X-ray band, there is a soft X-ray telescope which has X-ray optics and charge coupled devices. It is sensitive in the soft X-ray band 0.2 to about 8 kb. In the hard X-ray band, there is a payload LEX-PC, known as LEX-PC, large area X-ray proportional counters. It has 3 units and is sensitive in the 3 to 80 keV band. It has fantastic timing resolution of about 10 microsecond. In the hard X-ray band, and there is another payload or instrument called CZTI, cadmium zinc telluride imager. It is sensitive in the 10 to 250 keV hard X-ray band, and it is good for spectroscopy of the brightest X-ray sources. In addition, there is a sky monitor known as scanning sky monitor, which is sensitive in the 2 to 10 kb band, and it is essentially used to detect transient X-ray sources. AstroSat was launched on 28 September 2015 by PSLV rocket. This picture shows just before launch the integrated AstroSat, which weighs to about 1.5 ton. AstroSat had several advantages. Of course, it is a multi-wavelength astronomy satellite, and it is operating at low inclinations. So, this results in a low background. Most of the instruments produce continuous time tagging data, so which is very important to study fast variability, particularly with LEX-PC and CZTI instrument, which have microsecond time resolution. The soft X-ray telescope is very good for bright sources. This is actually helpful because other X-ray currently operating X-ray satellites are not good for bright sources. Their detectors gets saturated, while the soft X-ray telescope is excellent for bright sources, and one can study these bright sources using all the instruments in principle. One of the detectors, the instrument, the CZTI, also works as hard X-ray monitor above 80 kV. And as I mentioned, AstroSat can perform simultaneous observations over multiple wavebands from optical to hard X-rays. This is the coverage of this coverage of the AstroSat instruments at various bands. The UVIT, as I mentioned, it covers the visible as well as near and far UV bands. The soft X-ray telescope covers the soft X-ray band 0.2 to 8 kV. LEX-PC and CZTI cover the hard X-ray bands. These instruments are altogether are very useful to study various different classes of cosmic X-ray sources, like the active stars, supernova remnants, cataclysmic variables, neutron star and black hole X-ray binaries, clusters of galaxies, active galactic nuclei, including Seyfert's galaxies and blazars. Why multi-wavelength astronomy is important? Let me tell you the tale of this tale of the blind man and the elephant. So, the story goes like this. So, there is this animal which people found for the first time, and the blind men found the first time, and they are trying to find out what is this animal. So, essentially the blind men touch the various parts of this animal and they infer differently. Okay. So, this goes like this. For example, if you are observing in one band, then you infer certain aspect of the nature of the cosmic X-ray source. If you use different band, completely different band, you infer somewhat different aspects of the cosmic source. Unless you combine the information from different bands, then only you can infer the real nature or real physical nature of the cosmic X-ray source, just like by touching the various parts and combine all this information, then only one can infer the real picture. I will tell you some of the results from this Indian mission AstroSat. This is the ultraviolet imaging telescope image of the galaxy NGC 4593. This was taken with this UVIT, the NUV, near UV telescope, using one of the filters. This is a bright central region, essentially an active galaxy is here. So, when you study the X-ray radiation from the simultaneous AstroSat observation, you see the X-ray radiation actually highly variable. The same goes with far ultraviolet emission as well as near ultraviolet emission. Both the far ultraviolet emission and near ultraviolet emission are also variable. So, by studying the relationship between the variability in the X-ray band and in the UV band, one can infer important nature of this active galactic nucleus. So, essentially the physics of the accretion around this supermassive black hole. These observations demonstrate the timing capability of the Galaxy instrument. Here is the time series of this X-ray photons detected with Galaxy. You see here in the y axis, these are the X-ray photon counts per second. So, these are like 4,000, 6,000 ranges. So, essentially this detector is detecting so many thousands of photons every second, and these photons are detected with a time resolution of, as I mentioned, 10 microsecond. So, one can study very fine variability or very fast variability of these sources. And in this picture, what is revealed is that there are oscillations which are quasi periodic in nature. By studying some of these light curves of some of these objects, one is inferring that the variations are quasi periodic in nature. So, what is the origin of these quasi periodic oscillations? So, these are the important questions regarding these objects, which Astrostat mission is essentially probing. In this view graph, I show some results from the CZTI instrument. As I had mentioned, the CZTI an excellent hard X-ray monitor. So, therefore, it has detected a large number of bursts, the gamma ray bursts since launch. And localization of these gamma ray bursts are achieved using the shadows cast by the satellite structure. And by looking at the distribution of this Compton scattered events in the pixels of the CZTI, one can actually measure the polarization of this hard X-ray emission, which is something new and very challenging. And CZTI has been able to measure the polarization of some of these gamma ray bursts. So, to conclude, there has been very rapid progress in astronomy in the last years. So, if you look at the last 50 years, in the last 50 years, X-ray astronomy has progressed so much that optical astronomy took 400 years, and because of this reason, 2002 Nobel Prize was given to an X-ray astronomer Riccardo Giacconi. Using the most advanced X-ray satellites, it has been possible to study to make a detailed study of cosmic X-ray sources and their nature. Now, it is possible to detect X-ray emission from the farthest of the universe, and therefore contribute significantly to cosmology as well. X-ray astronomy is probing the most energetic phenomena in the universe. Without the X-ray astronomy or gamma ray astronomy, it would not have been possible to study such energetic phenomena. And with the Astrostat mission, India has exciting opportunities locally. These are some of the reference which one can actually study to know more about X-ray astronomy. So, thank you